The question is about compounds A, B, C, D and E and their interconversions. Some of these are shown in the diagram below. Give the names of compound B and C. So the first thing to do to be able to name them is to draw them out. So if we start with B, we've got a carbon with 3 hydrogens attached to a carbon with 2 hydrogens attached to a carbonyl group with a chlorine. As soon as you see this group, you know it's going to be an acyl chloride. So it's going to end in oil chloride. So the next thing to do is to see how long our carbon chain, and it's 3 long. So that means we've got propanoyl chloride. Then we need to have a look at C. Usually when you see something like this with 2 and an oxygen, you know you're dealing with an acid anhydride, and this is indeed an acid anhydride. So again, if we draw it out, then we've got our C double bond O, then this is the joining oxygen, and then we've got a mirror image underneath. So in the same way, we know we've got an acid anhydride, so it's going to end oic anhydride. To work out how many carbons are in it, just the 2 chains will be the same. So look at the top chain, it's got 3. So it's going to be propanoic anhydride. Propanyl chloride and all acyl chlorides, when they react with water, are going to react quite violently. In this case, you're going to get HCl formed, and you would see white, misty fumes. And those white, misty fumes would be HCl. Draw the reaction mechanism for the reaction of compound B with ammonia, showing clearly the graphical formula of the organic compound formed. So we've got B written there. If you want to, you can put the partial charges in. Doesn't have to be put in. So what's going to happen is we've got a partially positive carbon, so the lone pair from the nitrogen are going to be attracted to form a bond with the carbon. We've got both the oxygen and the chlorine, which are highly electronegative, pulling at the electrons from carbon. Think of this one as pulling with 2 hands and that one pulling with 1 hand. This has got the stronger pull, so this one is going to get the electrons. So they're going to move from the double bond onto oxygen. Make sure that you are starting the curly arrows either from a lone pair of electrons or touching a bond to show clearly where they're starting and where they're going to. The electrons are always going to be in the bond, not actually on the atom itself, unless it's a lone pair. So we now need to draw the rest of the structure. So the oxygen is now only attached by a single bond, but it's got the pair of electrons from the double bond that broke, and it's got a negative charge. The chlorine for the time being is still attached. The nitrogen, which had 2 a pair of electrons all to itself, has now shared that pair of electrons, which means it's effectively given one up, which leaves it with a positive charge. There's normally a mark for getting this structure right, so it's important to make sure you've got those charges. We now need to resolve it. So the first thing that's going to happen is this is going to come back down to reform the double bond. This bond is going to break and chlorine is going to take the electrons, and one of these bonds will break and the electrons will go on to nitrogen. It's important in this case to make sure we draw the final structure, because it specifically states, showing clearly the graphical formula of the organic compound formed. Okay, remember at the end we don't end up with HCl. Whenever we've got ammonia, we're going to end up with NH4 plus and Cl minus, which forms ammonium chloride salt. Not actually a mark for that in this question, it just shows the organic compound, but it's always worth putting in. It's always remember practicing putting it in as well. Compounds A, B and C will each react with the same alcohol to form compound D. Give the name of the alcohol and the name of compound D. So when A, B and C have reacted, they've all started off as propenyl chloride, or propanoic acid. They've all started off with this bit of the chain. So this is the bit that's been added. So this is the bit that's come from the alcohol. So the alcohol must have had that as the structure. Once you've got the structure, it's nice and easy to name. So the name is methanol. And the name of the ester, D, is going to be methyl, because we've got the short chain there, propanoate, because we've got the longer chain there. State the appropriate reaction conditions for the formation of compound D from each of the compounds A and B. So A is a carboxylic acid. So if we want to get an ester to form, we're going to have to warm it. And if you think back to when we did this as a practical, we added concentrated sulfuric acid. So the conditions for this one would have been concentrated sulfuric acid, and we want to warm it. B is an acyl chloride. Acyl chlorides react very readily and quite vigorously. So we don't want to put any temperature anywhere near it. So you would just do that that reaction at room temperature. Write the equation for the conversion of A to D. So we're starting off with the carboxylic acid. We know it's got to react with the alcohol, and the alcohol was methanol. And we know it's going to make our ester. And if you think about what's going on, we're going to be losing an OH and an H. So there must be another product. And that other product is going to be water. You just then need to check it's balanced. It is as it is, so we don't need to add any numbers. Name and outline a mechanism for the reaction between propanone and hydrogen cyanide. Sometimes it's easier to draw the mechanisms first, and then once you've got the mechanism drawn, you can go back and you can see which is the suitable name for it. So let's draw propanone. And it's reacting with hydrogen cyanide. So whenever hydrogen cyanide reacts with anything, it's going to be the cyanide ion that takes part in the reaction. If you're not sure where to start, think about your partial charges. This is negative, so it's going to be attracted to the carbon. At the same time, the electrons in the double bond are going to move on to oxygen. From the original hydrogen cyanide, we're going to have a H plus left over, so the lone pair on the oxygen are going to form a bond with that. So if we look what's happened, we've started with something that's a nucleophile, it's positive loving, and all we've done is add things onto the original molecule. So the mechanism must be nucleophilic addition. The main hazard of the above synthesis is we're using cyanide. Cyanide's particularly nasty. We'd say it's toxic. Carbonyl compounds can be reduced to alcohols. Write an equation for the reduction of propanone to the corresponding alcohol and identify a suitable reducing agent. In the equation, you may use the symbol H with square brackets for the reducing agent. Be careful to make sure you read the questions properly. Don't try and put things like sodium borohydride actually into an equation. So we're starting with propanone. There is absolutely nothing wrong with drawing the structure out if you feel more confident and you're less likely to miss something out. We're then going to put our hydrogen in square brackets. Now we're going to make an alcohol. So we're going to have a CH3, and then the carbon with the double bond is going to have a hydrogen added to it, and attached to the original oxygen there is going to be another hydrogen. So that means we've added 2 hydrogens to this molecule, one in the alcohol group and one attached to the carbon that had the double bond oxygen on it, which means we've got to make sure the equation is balanced. A suitable reducing agent would be sodium borohydride. It's also acceptable to put lithium aluminium hydride, but sodium borohydride is the preferred. Draw the reaction mechanism for the conversion of propanone to its corresponding alcohol. So you need to remember that sodium borohydride is a source of the hydride ion. The hydride ion is going to be interested in this partially positive carbon. So the electrons are going to go in and it's going to form a bond. At the same time, the oxygen will take the electrons from the double bond. The second step of this reaction is going to be protonation. That can be done with alcohol, water, a weak acid, and we'll get that final product formed. And we can see its reduction because we've formed an alcohol. By consideration of the intermolecular forces involved, explain why the product HCl is a gas, but the product CH3COOH is a liquid at room temperature. So molecules of HCl are going to have a permanent dipole in them. So they would be held together by dipole-dipole. Whereas here we've got an oxygen directly bonded to a hydrogen. So we're going to get hydrogen bonding. Hydrogen bonding takes more energy to break than dipole-dipole, therefore you get a different boiling point. Give 2 industrial advantages of using ethanoic anhydride rather than ethanol chloride in the manufacture of aspirin. It's going to be a less vigorous controllable reaction. And it's also a lot cheaper. Compound Y is an ester. State a common use for an ester. So you've got lots of options for this. They're used as plasticizers, they're used as solvents, perfumes, or flavourings. Propyl ethanoate is an ester that is structurally isomeric with compound Y. When propanyl ethanoate is heated with aqueous sodium hydroxide, 2 products are formed. Explain what is meant by the term structural isomer. So it has the same molecular formula, but a different structure, or a different structural formula. Give the name or structures of the two products of this reaction. So basically we're going to get a hydrolysis, we're going to get the molecule breaking off, and we're going to get the equivalent of a carboxylic acid and an alcohol. However, if we're using an excess of sodium hydroxide, as soon as a carboxylic acid forms, it's going to react with the sodium hydroxide to form a salt. So the first thing we would get would be sodium ethanoate. And the other product we're going to get is the alcohol, and you can see if it breaks here, the alcohol is going to be 3 carbons long. So it would be propan 1-ol. They will accept propanol. Name compound C. We've got an ester. This bit's going to give you the first bit of the name. So the first bit of the name is going to be propyl. The second bit of the name is going to depend on the length of this carbon chain, which is only 1 carbon chain long. So it's going to be methanoate. So propyl methanoate. Identify a reagent which could be used in a test tube reaction to distinguish between C and D. In each case, state what you would observe. Well, in this one, we've got an acid group. So any test that would detect an acid would work. In this group, we've got the equivalent of an aldehyde. But we've got the equivalent of carboxylic acid on the other side, so anything that would oxidise an aldehyde would also work and give a positive result. So there's a few options. You could test for the acid with sodium hydrogen carbonate. You would get no reaction with C, and you would get effervescence. You could use acidified potassium dichromate, and you would get orange to green with C, and it would stay orange, so you get no reaction. There are lots of other things you could do, such as universal indicator, reactive metal. You could also use phosphorus chloride, but I would say those two are the more common reagents. Name compound D. Compound D is a ketone, and it's got 5 carbons in the chain, and the double bond is on the second carbon. So it's going to be pentan 2-one. The number is essential because it could be pentan 3-one. E is a ketone, F is an aldehyde. So we want a test tube reaction that would distinguish between the two. So we're looking for tollins or phalings. Make sure you remember the correct result for both. So both of them would have no reaction with the ketone, and if you're using tollins, you would get a silver mirror with F, and if you were using phalings, you would get a brick red precipitate. Draw the structure of the chain isomer of F, which shows optical isomerism. So if we're looking at chain isomer, we're going to be leaving this functional group alone, and we're going to be messing with this chain. So if it's going to be an optical isomer, we need a carbon that has got 4 different groups on it. I'm going to go for this carbon, and I'm going to substitute the hydrogens for other things to give us a different chain. So we've still got our C double bond OH. We'll leave one of the hydrogens on there, and then we'll break off a CH3 from the end of the chain and put it on there. So that would just leave CH2, CH3. And you can see we've now got a carbon that has got 4 different groups around it. Glycerol is the byproduct in the formation of soaps from fats by hydrolysis. Draw the graphical formula for glycerol, propane 1,2,3 trial. This one says graphical formula, so we're okay. If it says displayed formula, you've got to remember to show every bond, so you would need to show the bond between the oxygen and the hydrogen. It's probably good practice to do that each time, and then you don't get caught out. What is the name given to the process? Well, for making soaps, it's called saponification. Explain how sodium stearate, or sodium octadecanoate, is produced from a suitable fat by hydrolysis. We would hydrolyse it in alkali conditions. So something like sodium hydroxide. And the ester bond would break. And that gives us the sodium salt. Explain what structural property gives it of sodium stearate leads to it to act as a surfactant. Surfactant is a soap. So it's got an ionic end which will dissolve in water, which is hydrophilic. Philic meaning love, so it loves water. And then it's got a carbonyl part which is hydrophobic. So the hydrocarbon part of the chain is hydrophobic, which means it will dissolve in fat. Scientists have been considering the use of biodiesel as an alternative to diesel in this process. Methyl esters are produced from glycerides such as rapeseed oils. Consider the following reactions. Explain why an excess of methanol is required. Well, if you have a look, we have a reversible reaction. If we put an excess of methanol in there, the system is going to try and reduce the amount of methanol by moving the position of equilibrium to the right, which is going to give you a higher yield of glycerol. And of course a higher yield of the methyl ester, which is biodiesel, which we're trying to produce. The advantages of producing a methyl ester as biofuel, rather than leaving it as the glyceride, is that it's less viscous, so it's going to work better in an engine. Explain why biodiesels are classified as carbon neutral. There's no net production of carbon dioxide. So as the plant photosynthesizes and grows, it's absorbing carbon dioxide, and that's going to be the same amount that is given out when it's burnt as a fuel. If there are any questions that have been gone through in this walkthrough that you still don't understand, it is essential that you bring them and ask your teacher, or bring them to a workshop and ask somebody to go through it with you. Any of these questions could easily come up on the end of your exam, so it's essential that you understand all of the answers.